This video describes a mathematical technique for finding the trend line through the plotted points of a calibration curve. Assuming that the calibration curve for an analysis is linear, we proceed to plot the data points, where the coordinates of each data point I is given by x sub I and y sub I. We then do the following. We find the best straight line through these data points. We'll call this line the best fit line. This is done by using a mathematical technique called linear regression, or the method of least squares. The equation for the best fit line is given by the equation y equals m times x sub I plus b, where m is the slope of the line and b is the y-intercept of the line. X sub I is the x-coordinate of point I. Y is the calculated value of y for a point on the best fit line with an x value of x sub I. In the points of a calibration curve plot, there is random error in the y variable, but there is a negligible error in the x variable. Now we speak of the vertical deviation, or d sub I, for a given point. This is the difference between the y-coordinate of an experimental data point y sub I and the y-coordinate for the point on the best fit line directly above or below the experimental data point. The method of linear regression works by finding the line that minimizes the vertical deviations in the plot. Specifically, it does this by minimizing the sum of the squares of the vertical deviations. Let's examine the mathematics for this. The vertical deviation d sub I for point I is given by equation 1. The sum of the squares of the vertical deviations, let's call it q, is given by equation 2. To find the minimum in q, we take the derivative of q with respect to the two parameters in the equation of a straight line, the slope of the line m and the y-intercept b. So what we next do then is set each of these derivatives equal to 0 and then solve for m and b respectively. Now the basic idea here is that the derivative of a function gives the slope of that function at any given point. The minimum in the function is the point where the slope equals 0. So we take the derivative of q with respect to m, set it equal to 0. Take the derivative of q with respect to b and set it equal to 0. And this will lead to two equations, and we're assuming here n data points. The two equations are respectively equation 3a and 3b. Now the next step is simply to algebraically simplify equations 3a and 3b. This leads to the following two equations, equation 4a and 4b. Next, we solve these two equations, 4a and 4b, simultaneously for m and b. This leads to the following algebraic expressions for m and b respectively, equation 5a and 5b. Now both the equations have a common denominator d, and d equals the expression shown here. All right, next I want to show an example where we will use Excel to find the best fit line through data points by solving the least squares equations that we previously derived, namely equation 5a and 5b. I've entered coordinates for 4 data points in columns B and C, shown here. These points are known to follow a linear correlation. So let's go ahead and plot these points. I'm going to click on the Insert tab, go over to the Charts section, and choose this icon, Insert Scatter, and pick the this one here, the first one. So we have now a plot of our 4 data points. We note that the 4 points appear to follow a straight line, but not exactly, and that's because of error in the points. Now our task is to find the best fit line through these points and obtain the equation for this best fit line, namely to get values for the slope and intercept of this line. And as well, we'll obtain statistical error information for the slope and intercept and more. So the equations for slope and intercept are shown here. That's for the slope, and here for the intercept. Those correspond to equations 5a and 5b respectively. Each of these equations is made up of terms that consist of sum terms, product terms, involving the coordinates x and y. So what I've done in the Excel spreadsheet is evaluate the key terms, the required terms. So in columns B and C we have our data for our 4 points. Column B is headed x sub I, those are all the x coordinate values for the data points. Column C, the heading is y sub I, those are the y coordinate values for the data points. An important row is row 6, where we're going to use a formula to calculate the total of the values in the columns. So in column B6, for example, using the Excel built-in sum formula, I've got the sum of the x-coordinate values for those 4 data points. And in row 8, this is a convenient label for each of those quantities we're going to calculate. All right, column C, those are the y-coordinate values. I want to compute the sum of the y-coordinate values, and I'm doing that in cell C6, and there we're using the formula to do that. The sum of cell values C2 to C5. I'll also need the product values of the x and y coordinates for each point, and that's in column D. I'm using a formula to calculate the product values in cell D2, D3, D4, D5, and then I'm going to, or I have rather, computed the sum of the product values x and y by using the built-in sum formula. Another term I'll need is the square of each of the x-coordinate values. That's in column E. Here's our heading. And so I'm using a formula. I wrote a formula to compute each of those squared values. For instance, the coordinate value for point 2 is 3. I want to compute the square of that. And I'm doing that by taking the value in B3 and simply squaring it, B3 caret 2. So each of these cell values has the square of the x-coordinate value. And then in cell E6, I've got the sum of all those squared x values. All right. Now in column G, this is the formula for the fitted line, m times x sub I plus b. And of course I'm using a formula to compute the values for that expression. This formula calculates the corresponding value for point 1, point 2. The formula calculates the value for that equation for point 2 and so forth. Remember, we mentioned earlier the vertical deviation for each point. That's denoted by d sub I. And d sub I is the equation for that is shown here in the heading cell. The yi value minus the evaluation of the expression mxi plus b. And in each of these cells, I'm using a formula to calculate that. So for point 1, the vertical deviation is 0.0385. For point 2, the vertical deviation minus 0.1923, and so forth. Another key term that I'll need is the square of each of those vertical deviations, and that's done in column K. So the square of each of the vertical deviations for each point, I'm using a formula to do that. And for example, point 1 in cell H2, I've computed the value for that vertical deviation, and correspondingly in cell K2, I use a formula to take the square of the contents of H2 to give me the square of the deviation. And correspondingly, we've got the formula to calculate the square of the deviation for point 2, point 3, and point 4. And importantly now, I want the sum of the squares of the vertical deviations, and that's given in cell K6. And there's the formula to do that. Sum of the values from K2 to K5. And there's our value for the sum of the squares of the vertical deviations. All right. So those are the values for the parameters I need basically to evaluate the slope and the intercept. Let's first look at the slope. There is the general equation. I think that was called equation 5a in the derivation. If you look at each of the terms, it's the quantity of n times the sum of the product xy minus the product of the sum of xi times the sum of yi, and it's divided by d, called the denominator value. Now the denominator value we previously showed, and that's given by the expression here, n times the sum of the squares of xi minus the square of the sum of xi's. Alright, now since we need the d value for calculating the slope and the intercept, in cell C12 I use a formula to evaluate the value of the denominator, and that comes out to 52. Now in cell G12, here's the formula that corresponds to what's fully shown here, and we're using the formula in cell G12 to do that. When you use the formula, you get the slope value 0.6154. All right, to get the value of the intercept, I'm calculating that in cell M12, and there's the formula that will do that. And when you evaluate the formula for that, you get 1.3462. So that gives us the desired slope and intercept, y-intercept values for the best line through the points, the best fit line. Now, here's our plot. Excel has a nice feature that finds the best fit line, and it does. We can do that as follows. What you're going to do is do a right click on any data point, and then choose the option Add Trend Line. Now when I do that, the format under Chart Tools appears, and shown on the right, we've got the panel here which allows doing some detailed evaluations with respect to the trend line. The default is linear, and if you had a different function, exponential function of course, then you could choose that option. So it's that's the default, and it's already drawn in the line. This is the best fitted line, and if you can get something that's very useful, go down and click on this box that says Display Equation on the chart, and there it is. There's the equation of the best fit line. Let me move it over a little bit, and you can see nicely that it's of the form y equals mx plus b. It's got the value of the slope 0.6154. That agrees exactly with what we evaluated up in cell G12. The y-intercept value that it returned, 1.3462, also agrees exactly with what we evaluated with the formula we wrote for cell M12, 1.3462. Now you can also, if you go back and do a right click on the trend line, you can massage that line, the graphic display of the line. What I want to do now is go over under the Format Trend Line panel choose that paint can, and let's see, select solid line, and let's see, right now it's the default is the dash type, but if you go down to this, click on that and choose the image for the solid line. We'll note that our plot now turns into a solid line. I kind of prefer black, so let me change the color. Click on the color icon, click on the little black square, and of course our line now turns black. And I kind of like a narrower line, so I can get that by going to the width control and lowering the point value. And there it's a nice looking solid straight black line. All right. Now the Excel spreadsheet allows you to get more information, namely error parameter values. We can get the standard deviation and the slope and the intercept, and let me now show you how that's done. Down here in this section here, I have the formulas for calculating the standard deviations of those parameters. The starting point is actually this. If you look at this equation here, it's called S sub y. That's the standard deviation in the vertical deviations of y. And the formula for doing that is presented here. It's the square root of the ratio, the sum of the squares of the vertical deviations divided by the total number of degrees of freedom, n minus 2. N, remember, is the number of data points. And that gives us the value for the standard deviation and the vertical deviations. I've evaluated that in column M19. There's the formula that does that, using our built-in square root function, the square root of the quantity K6. That's right here. That's the sum of the squares of the vertical deviations. It's going to be in our numerator. And our denominator is the value in K5. Excuse me, I'm sorry. Our denominator is given by M7 minus 2. The value in M7, that's the total number of data points minus 2. So basically it's just 4 minus 2 there. That's the total number of degrees of freedom. So then the formula takes the square root of that ratio, and that comes out to 0.19612. That particular error parameter, SY, is going to be used in the equations to calculate the standard deviation and the slope and the intercept. The standard deviation and the slope is given by the equation here. That's S sub m. It equals the SY, the standard deviation, vertical deviations, times the square root of the ratio n divided by d. And that formula is used in cell M21. There it is. And the formula generates the value for the standard deviation of the slope that comes out to 0.05439. The standard deviation for the y-intercept b, the formula that does that is in cell M23, and the equation for that is shown here. That's sy times the square root of the ratio of the sum of the square of xi's divided by d. And those error parameter values are very informative and very useful. All right, that completes the example of how we can use Excel spreadsheet to evaluate the slope and the intercept of the best fit line, as well as getting the standard deviations for the slope and the intercept. Thank you.